In this tutorial, we are going to use R to build a simple linear model and analyze the code output. Let's start by loading the CSV data. The table shows the columns with the pollution count, the regression variable, and the purity, the response variable. The next step is checking the data structure. We can see that both variables are numerical, so we are good to go. Now, let's build a linear model for purity as function of pollution. The linear model's output for purity as a function of pollution count shows the intercept, beta 0, 96.5, and the slope, beta 1, negative 2.9. These values are used to build the regression model, purity equal to 96.5 minus 2.9 pollution count. Now we are going to look into some extra information on the output of the LM function that we have been overlooking until now. For each regression coefficient, we also have the standard error. The standard error measures how far the calculated coefficients can be from the real ones, those that would have been estimated if we had an infinite number of observations. And in the last columns, we have the results of a t-test for each coefficient. The t-test is the statistical test that will give the information about the significance of each regression coefficient. The null hypothesis H0 is rejected if the t-value or t0 is higher than a critical t. The last column shows the p-value of each coefficient, stating their individual significance levels. In this example, both coefficients are significant. The following information is the R-squared. The R-squared is the determination coefficient, and it measures the proportion of the total variability of the data explained by the model. It is calculated as the ratio between the sum of squares of the regression model and the total sum of squares. The sum of squares of the regression measures the data variability due to the model, while the total sum of squares measures the total variability in the system. Both sum of squares are estimated by matrix operations. In our example, the R-squared states that the model explains 87.4% of the data variability. And finally, let's analyze the last row of the linear model output. It has the information on the F statistic value, the degrees of freedom dF, and the p-value. These are the results of the analysis of variance of the model. The ANOVA table of the regression model splits the total variability of the data into the model and the residuals. As we have just seen for the sum of squares of the model and the total sum of squares, the sum of squares of the error can also be estimated using matrix operations. The model has p-1 degree of freedom, where p is the number of parameters in the model, 2 in this example. The total degrees of freedom is always the number of experimental observations, capital N, minus 1, and the degrees of freedom of the error is the difference between them. The ratio between the sum of squares and the degrees of freedom is the mean squares. The mean squares of the model is a point estimator of the variability due to the model, and the mean squares of the residuals is a point estimator of the variance of the system due to the noise or experimental error. The analysis of variance performed by the F-test compares the variance explained by the model, the mean squares of the model, with the variance due to the experimental error, the mean squares of the error. It is the ratio between the mean squares of the model and the mean squares of the error. The hypothesis testing the analysis of variance of the regression determines whether a linear relationship exists between the response and the regression variable. The appropriate hypotheses are H0 or null hypothesis, beta 1 is 0, meaning that the regression variable does not affect the response, and H1 or alternative hypothesis, beta 1 is different from 0, meaning that there is a relationship between the regression variable and the response. We will accept or reject the null hypothesis based on the p-value, determined from the f0 and the degrees of freedom of the model and the residuals. The p-value is the smallest level of significance alpha that the regression is significant. The null hypothesis h0 will be rejected if the p-value is lower than the significance level, usually 0.05. So let's go back to the linear model output and use the information on the analysis of variance of the model to fill the ANOVA table. We have the degrees of freedom, the f0, and the p-value. The p-value of 3.3 times 10 to the power of negative 7 shows that the regression model is highly significant. This whole information may seem a little exaggerated. However, it is essential when dealing with multiple regression variables, as we are going to see shortly. The next step is to perform the residual analysis. The first code line creates a grid of 1 row by 3 columns for the plots. In the next code lines, we are going to build the residual plots with the experimental results, the purity column in the pollution dataset, with the predicted results, the fitted values from the model, and with the regression variable, the pollution column in the pollution dataset. Let's run and analyze them. The resulting residual plot shows that the residuals have a random distribution. Finally, as our model is significant, with a low p-value, a high R-squared, and the residuals have a random distribution, we can build the final visualization of the results. We are going to build a scatter plot with the experimental data and add a straight line for the regression model. The first code line creates a grid of 1 row by 1 column for the plot. It is necessary because we have previously created a grid of 1 row by 3 columns for the residual plots, and R keeps this information stored. The second code line creates the scatter plot of the experimental results, and then we have the x and y-axis titles. The last code line creates a straight line using the ab-line function. The first argument is the intercept, beta 0, in our example 96.4546, and the second argument is the slope, beta 1, negative 2.9010. Those are the values that we calculated previously. Let's run and analyze the output. The resulting plot shows the experimental data and the regression model. The slope of negative 2.9 means that the expected decrease in the oxygen purity is 2.9% when the pollution count increases by 1 ppm. The intercept means that the expected value of oxygen purity when the pollution count is 0 is 96.5. But wait, if the pollution count is 0, should not the purity be 100%? Why it is only 96.5%? First, the R-squared is 0.874, meaning the model explains only 87.4% of the variability. The pollution count does not explain around 12.6% of the purity behavior. The second and fundamental reason is We don't have observations with pollution near zero. We don't know if the model is still valid for very low pollution count. Maybe the relationship between purity and pollution count is different there. Now, something that you should always remember. We must never use empirical models to conclude outside the range of the regression variables. Empirical models are only valid within the range of the tested explanatory variables.